Okay. Welcome back, everybody. Welcome back to another exciting session of CE 374U. Just a quick announcement before we get started. We're not going to be using ArcGIS for the first 20 or so minutes of class. So you can just have your laptops closed for now, just to conserve your battery. I brought in some power strips. There's only like 3 power outlets in this room. So I will have enough outlets for, I think, 18 people or 18 computers. So we'll figure that out when we come to it. But for the first 20 or 30 minutes or so of class, I'm finishing up our module in hydrology, which you'll need for the homework. Okay? Okay. Could I get everybody's attention, please? Could I get everyone's attention, please? Thank you. Okay, so a couple quick announcements before we get started. Homework 2 is due Thursday. I have office hours today at 5:30 as usual, and I can use that time to help answer any questions about the homework that you may have. And as I mentioned last week, we're going to be doing in-class exercises with ArcGIS this week. I posted some data sets in the announcements. None of these are very large, but I would recommend downloading these ahead of time if you haven't done so. There are, I think, 6 data sets here. So go ahead and download those beforehand when we get to the ArcGIS portion of the class, okay? Are there any questions before I move forward? And when we transition to ArcGIS, we can help anyone who's having technical issues installing or anything of that nature, okay? Okay, great. So before I get started with ArcGIS, which is what is going to be our main focus today, I want to finish up the last few parts of our module on hydrology, which you will need for the homework. So recapping from last time, during the last lecture, we talked about 2 topics. We talked about unit hydrographs, and we talked about how to use unit hydrographs using an operation called convolution. Can anyone kind of explain to me what the gist of a unit hydrograph is? What's the point of using a unit hydrograph? So first of all, what are we trying to compute when we use a unit hydrograph? What are we trying to compute when we use a unit hydrograph? Right, so we're trying to compute the runoff response from a watershed. So what does a unit hydrograph allow us to do? Kind of in just a sentence. Does anyone have a guess? Yes.
Calculates the runoff based on how delayed it is for cycle precipitation.
Yeah, so what a unit hydrograph allows us to do in a word is to compute the runoff response of a watershed for any arbitrary rainfall input. Okay, so if we have a sequence of rainfall occurring over time, it can compute that runoff response from that arbitrary rainfall input. What does a unit hydrograph represent? Yes.
Travel time is the farthest drop.
So the unit hydrograph represents the travel time distribution of the watershed. The travel time of the farthest drop is something I will mention this time. That's called the time of concentration. But the unit hydrograph represents the travel time distribution of a watershed. The central idea behind a unit hydrograph is a unit hydrograph represents the response of the watershed to an instantaneous unit impulse of rainfall. And using that unit hydrograph, you can compute the response of the watershed to an arbitrary rainfall input, okay? So you compute the response of the watershed to a unit impulse of rainfall, and then you can compute the response of the watershed to an arbitrary rainfall event using an operation called convolution. And in the last class, we kind of showed you one way that you could apply convolution to represent the response of a watershed. I wanted to finish up our discussion on convolution. So this is a problem that's in the homework. And I showed you how it essentially consisted of scaling the unit hydrograph by each element of your precipitation time series and kind of stacking them up. There's another way that you can think of convolution, and that is you can essentially think of convolution as a fancy moving average. Okay, so if you have your precipitation input here, which we'll call PT, and you have your unit hydrograph UT, which you are convolving it with. In this case, we have our precipitation input defined at times 1, 2, and 3. So this would be P1, P2, P3. And we have our unit hydrograph defined at 3 points, 1, 2, and 3. And the unit hydrograph is simply equal to 1/3 at each time step. What you're going to get when you convolve your rainfall input with this unit hydrograph is essentially what will become the moving average of the rainfall. Okay, so I'm going to go through this operation step by step, just so you can see how it works. Okay, so we're going to be using this definition of convolution that I gave you in the notes. So this is the output of the rainfall input P convolved with the unit hydrograph U. Okay, and it's going to give us the discharge Q at time index N. So let's compute this for each time index in our output. Okay, so what we're going to do is we're essentially going to take our unit hydrograph, we flip it around, and then we're going to slide it over our precipitation input and essentially compute the weighted sum of these elements as we move U over P. Okay, so I'll show you kind of visually what this looks like. Okay, and I started this at the last part of class last time, but I'm going to finish it now. Okay, so we take U, we slide it 1 over. Okay, so that U1 and P1 are now overlapping. Okay, so here you get, let's just say U1, P1. Okay. Your discharge output at time step 1 is going to be P1, U1, which is equal to 3 times 1/3. If you go back and look at the plot on the last slide, okay, which will give you 1. Okay, so moving to the next step, we slide U over by 1 to the right again. And we line them up. And so here we will have U2 P1, and here we will have U1 P2. Okay, so our discharge at time step 2 is going to be P1 U2 plus P2 U1, which is equal to, let's see, 3 times 1/3 plus, what is P2 again? That is 1 times 1/3. And that's going to give us a result of 4/3. Okay, so that's the discharge at the second time step. Okay. The third time step, you can kind of see the pattern again. We slide our unit hydrograph 1 over to the right, and now they are completely overlapping. Okay, so now we have U3 P1, we have U2 P2, we have U3. Sorry, is that right? So sorry, that's U1 P3. Okay, yeah, that's why they call it convolution. Sometimes you get a little bit convoluted. Okay, so we'll end up with discharge at time 3 is equal to P3 U1 plus P2 U2 plus P1 U3. Okay, and we can see all of them are going to have a factor of 1/3, so I'm just going to pull that out. Times 3 plus 1 plus 2. So that's P1, P2, P3, 3, 1, and 2. And what that'll give us is result of 2. So the discharge at time step 3 is 2. Okay. Let's just finish this out. Okay, we can slide over 1 more to the right. Now P1 is going to be over here. P2, P3. Let me just write this out. This is P2, U3. This is P3, U2. Q4 is going to equal P2, U3 plus P3, U2, which is equal to 1/3 times 1 plus 2. And this is equal to 1. I'm going to give you a second to write that down before I switch to the next page. But you can kind of see what's happening here, right? When we're sliding this unit hydrograph over our precipitation input, in this case, because U1, U2, and U3 are all equal to 1/3, what you're taking is the moving average of the precipitation input, right? And that's why we end up with these expressions here. Here you have 1/3 times 3 plus 1 plus 2. This is taking the moving average when they're both completely overlapping, right? Yes. So this is, I'm just giving you this example unit hydrograph. So this is a simplified example just to show you it's essentially equivalent to a moving average when the unit hydrograph is flat, essentially, when it's just a constant value. Yeah. Yes, so that's what we're gonna show you in the next part. On the homework, I give you a unit hydrograph explicitly to do this on. Okay, so let's do this for the final step. Okay, we move our unit hydrograph over 1 to the right again. And now we have only this one overlapping. Okay, so this is U3, P3. And our discharge at time step 5 is equal to P3, U3, which is equal to 2 times 1/3, which is equal to 2/3. Okay, so let's go ahead and plot out the results. What will this look like? Okay, so let's say we have 1, 2, 3, 4 on our time axis. On our y-axis, this is the discharge. Five, 6, so we have 1/3, 2/3, 1, 4/3, 5/3, 2. Okay, so if we go back and look at our discharges at each time step, we have 1, 4/3, 2, 1, and 2/3. Okay, so our resulting discharge hydrograph will look like the following. We have 1, 4/3. Let me draw that a little bit more. 1, 4/3, 2, 1, and then 2/3 is our final. Okay, so this is essentially what HEC-HMS, for instance, will do if you give it a unit hydrograph for a watershed and a rainfall input. So assuming they're both discrete, it will compute the resulting runoff response by convolving the two signals together. Okay, and you can see in this case what we produced when our unit hydrograph was just a constant value is essentially the moving average of the precipitation input over time. Yes. There's Q5 as well. So after Q5, they won't be overlapping. And before Q1, they won't be overlapping. So anytime that they're not overlapping, you treat it as a 0, basically. Yeah. So note that in this case, it's actually, it's literally the moving average, but our unit hydrograph doesn't have to be a constant function, right? It could be, for instance, you have a smaller value at the exterior points and a larger value in the middle. Let's just say this larger value in the middle is 2 times the exterior points. And then what you would have is essentially a weighted moving average where the interior point is weighted twice as much as the exterior points. Okay, so you can think of convolution, which we are applying using the unit hydrograph method, as essentially producing a weighted moving average of the precipitation. Okay, so that should give you what you need for your homework involving convolution of the unit hydrograph with a precipitation input. Are there any questions on this process? Any questions? Well, is anyone taking a look at this homework problem yet? Yeah, okay. Cool. So the next question, and a question which one of you just brought up, is how do you create a unit hydrograph? Let's just say, how do you make a unit hydrograph? So if you were a consultant and someone asked you to produce a unit hydrograph for a watershed, how would you do it? What would you try? Sorry? Excel? That's a good answer. It's always a good answer if you're a consultant. So what is a unit hydrograph again? Sorry? Yeah, so it'll compute the runoff. What did we say the unit hydrograph represents at the beginning of class? Yes.
A way to model the runoff response arbitrary.
Right. So what's another kind of identity for the unit hydrograph? What is it? Someone said it earlier in class today. Yes.
How long it takes water to get to the channel?
Yeah, so it represents the travel time distribution of a watershed. So how might you go about computing a unit hydrograph if you have, for instance, maybe some GIS data of a watershed? How might you do that? Any ideas? Yeah.
If you like split it up and find how long it takes from each like individual section.
Yeah, so that would be an excellent way to compute the unit hydrograph for a watershed. Okay, so you could split it up. Maybe you can split it up into little pixels. You can split it up into little pixels, and then you could find the travel time of the water as it moves through each of these paths. And what you would end up with is essentially a histogram of the travel times throughout the catchment. Okay, so that would be a great way to compute the unit hydrograph of a watershed. But in practice, this isn't how they do it most of the time. What they do most of the time is essentially assume that the unit hydrograph conforms to a certain shape. And the method that I will be showing you, the SCS unit hydrograph, essentially assumes that the unit hydrograph conforms to the shape of a triangle. Okay, so it's assuming that this travel time distribution is roughly similar to a triangle in shape. Okay. Cool. All right, so I'm going to go through the process of using the SCS unit hydrograph method. So this is largely an empirical method. Essentially, what it does is it uses a large number of empirical studies to essentially approximate what the unit hydrograph of an average watershed might look like. And it kind of tabulates those values in a way that allows you to apply this method to a watershed of your choice. So I'm going to go through the procedure here, and I'm going to go relatively fast because I want to reserve most of the time in class today for the unit hydrograph, but I want to make sure that you have enough here to do the homework problems. But it essentially is a way to compute the unit hydrograph or approximate the unit hydrograph for a given watershed, assuming you know some parameters about the watershed, okay? Okay, so the SCS unit hydrograph method, it can assume one of two forms. So it can assume the unit hydrograph is either roughly triangular in shape or curvilinear in shape. What I'm going to show you in the method you'll use on the homework is the triangular shape. Okay, so on the x-axis here, this will be time divided by the time to peak. So that is going to be our x-axis. The y-axis is going to be Q, the discharge, divided by the peak discharge. Okay, so this is kind of normalized to the peak discharge and to the time to peak. Okay, so let's see here. Let me just divide up this x-axis. So this is 1, 2, 3. So at 1 on the x-axis, you will have that t is equal to the time to peak. So this will represent the peak of the unit hydrograph. And let's just say our peak corresponds to this point here. Okay, so the unit hydrograph will, let's see what color, I'll do it in white. The unit hydrograph will look like this. Okay. And it will be triangular in shape, and it will intersect back with the x-axis at a point of about 2.67. So let me actually use this here. So this is our shape for the unit hydrograph. So note, this represents the peak. And there's a couple components here we have to label. Let me just draw the dimensions in green here. So note that this here represents the time to peak. So TP is time to peak. This component of the triangle here, this is the recession time. And if you add both of these together, you get what's called the time base, TB. Okay, so this is essentially the base of the triangle. Okay, so the SCS unit hydrograph also assumes a rainfall input that looks like this. So this is a rainfall input. We're just drawing it up at the top here. And the rainfall input has a duration, let's call it T capital R. Okay, this is the duration of rainfall excess. And it also assumes what's called a lag time. So it's the distance from the center of the rainfall event to the peak of the unit hydrograph. So this I will label as, I'll just do it right here. This is TL, and this is the lag time. Okay. All right. There's one more concept I have to introduce before we can get into the empirical equations that SCS uses for computing this unit hydrograph. And that is TC, or the time of concentration. Okay, so in hydrology, TC often denotes the time of concentration. Okay. And the time of concentration essentially represents the travel time from the furthest point in the watershed. Okay, so let's say that the furthest point in the watershed is here. This is the point that it takes the longest for water to travel to reach the outlet. Okay, so the water would have to travel, for instance, all the way through here. And as such, it would represent, on our histogram of travel times, it would represent the final point. So the time of concentration is significant because it's the time at which, if you have a prolonged rainfall event, it's the time at which the entire watershed will be contributing to the discharge, right? If you have essentially a rainfall event that's just kind of pouring water on the watershed at a constant rate, the time of concentration was represent the time at which the entire watershed is contributing to the discharge at the outlet, and thus the time at which you will see the peak discharge at the outlet for a prolonged rainfall event. Okay, so TC is the time of concentration. What we need to define the unit hydrograph is the following. We need the dimensions of TP, the time to peak. We need TB, the time base, or TR, the recession time. And we need QP, okay, the peak discharge, which corresponds to this point right here. Okay, and the SCS method gives us empirical equations for computing each of these, okay, which I will give to you. I'm going to go through this relatively fast because one, I want to make sure we have enough time for ArcGIS. Two, there's not really much of an explanation behind a lot of these empirical equations. They are just kind of assumed to be the case, okay? Okay, are there any questions on SCS unit hydrograph before I move on? Yes?
I'm confused about what the excess rainfall chunk.
Yeah, so the SCS unit hydrograph is defined with respect to a excess rainfall event, which has some duration to it. Now note that this makes it so that it's not technically a unit hydrograph in the way that we've discussed before, because before we assumed that the rainfall was instantaneous. The rainfall needed to produce the unit hydrograph was instantaneous. But the SCS method assumes a rainfall event with some discrete duration to it. Yes?
So what's the lag time? Is that like from the start of the storm or from like the end?
Half. It's from the halfway point of the storm event to the peak.
Oh, so high up.
The rainfall?
Yeah.
So it's on you can think of it as being on a different axis.
Oh.
It's rainfall. So it's usually when hydrologists draw the discharge and the rainfall, they draw the rainfall up on top and then the discharge on the bottom, I guess, because rainfall comes from the sky and discharge occurs on the ground.
Fair enough.
So, yes.
The TC, where is that?
So I didn't want to draw it on here because it actually would kind of confuse things.
Okay.
Like I said, this isn't technically a unit hydrograph in the way we've defined because the rainfall event has a duration. But if you draw the curvilinear unit hydrograph, so there's two versions of the unit hydrograph. One is the triangular, one's the curvilinear. The TC would be the essentially the duration from the end of the rainfall event to the inflection point on the curve. Okay, so don't worry about this here. This is just how the SCS method defines it. Think of the time of concentration as being the time it takes for the furthest part of the watershed, for a drop of water on the furthest part of the watershed to reach the outlet. Okay. Okay, so let me give you the empirical equations for the SCS method. You can use this to essentially compute this unit hydrograph, which you'll need for the homework. So the SCS method assumes the following. So first, from empirical studies, the time of concentration and the lag time are related as follows. The time of concentration is equal to 5/3 times the lag time. Okay. The time to peak is assumed to equal the half of the rainfall duration plus the lag time. And finally, from other empirical studies, the rainfall duration is assumed to be 0.133 times the time of concentration. I can't give you an explanation for why these equations have these values. They are just from empirical studies. Okay. Okay. So what this gives you is the following values for the time to peak and the time base. Okay. If you have the time of concentration, you can compute these values. So the time to peak will be equal to 0.67 times the time of concentration. And the time base will be equal to 2.67 times the time to peak, okay, from our drawing earlier. So with these two values, you can construct the dimensions of the x-axis of the unit hydrograph. All you need is the time of concentration, which in the homework will be given to you, but which you can also compute using other empirical equations. Okay. And similarly, the time of the receding limb is simply equal to the time base minus the time to peak. Okay, so another fact you will need to know for the homework. So if we look at this unit hydrograph here, I'll give you another second to write that down. And this is in the type notes as well. Okay. So another fact to note about the SCS unit hydrograph, the volume of direct runoff is equal to the area under the unit hydrograph, right? So it's a triangle, so we can compute that as 1/2 the base times the height. So the volume of runoff is equal to 1/2 times QP, the peak discharge, times the time to peak plus the recession time. So note this is the volume of runoff. So this is in units of volume, like cubic feet. This is the peak discharge. And this is essentially if you combine these together, this is the time base, this is the base of the triangle. Okay, so you can compute the volume of runoff. What we're going to do here is we're going to rearrange this for the peak discharge. Okay. So if we rearrange this, we get that QP is equal to V divided by TP times quantity 2 over 1 plus TR divided by TP. This is just rearranging that equation we had before. And what we can do is we can take this entire quantity here. I know I'm going quickly, but I want to make sure we have enough time for ArcGIS. We can take this entire quantity here, and we can just call this entire part in parentheses. We can call it K. And we get that QP is equal to KV divided by TP. Okay. So what is typically done in the SCS unit hydrograph method is they have a set of units that that is conventionally used with. And so this is often converted into those units with our coefficients defined for those units. So if we want the peak discharge to be in units of cubic feet per second, let's just write this down. Okay. We want QP in cubic feet per second. And we have excess precipitation in inches and area in square miles. Okay, it's often rearranged as follows. And this is the form you'll be using on your homework. It's rearranged in the following form. QP is equal to C times A times Q over the time to peak. And I'll define each of these, okay? So QP, this is the peak discharge in cubic feet per second. Okay, TP, again, this is the time to peak in hours. Q doesn't have anything to do with discharge, actually. This is the essentially inches of rainfall. So this is the inches of excess precipitation. I'm just going to call it volume of runoff per unit area. Okay, and this is in inches. A is the area of the watershed. And this is in square miles. Okay, and C is essentially a constant that converts between units. And for the unit system we're using, this will be a value of 484. Okay, and it will convert the units accordingly. Okay, so I just want to make you aware of this for the homework because it can be a bit confusing if you don't know where this equation comes from. It's essentially converting between different units, okay? Yes. No, yeah, SCS likes to have things in weird American units. And so this is the units for this equation, okay? It's written in this way so that the area is in miles squared, the volume of runoff per unit area is in inches, the time to peak is in hours, and the peak discharge is in cubic feet per second. So this equation is meant for those units, yes. Okay, great. Are there any questions on SCS unit hydrograph before we move on? Yes. Yeah, so yeah, they're meant to be used together. So you use the SCF's curve number method to find the excess precipitation, and then you use the unit hydrograph to route that precipitation over the landscape, essentially. Yeah. Yes. Yeah. Okay, great. With that, I'm going to transition to the next part of the class where we'll be using ArcGIS. So go ahead and get your computers out. And Becky, could I get your help? I brought a couple power strips. So let's try to distribute these roughly evenly across the collection if possible. Okay. So I'm going to go ahead and get started. Okay, I'm going to go ahead and get started. So I have ArcGIS opened up. So ArcGIS is probably the most commonly used geographic information system software. These are software essentially used for analyzing geospatial data, creating maps. They're a really big part of what I think should be a big part of the civil engineering curriculum. ArcGIS is probably the most popular. There are some open source versions that also work on Mac and other platforms that I can talk to you about, but ArcGIS is probably the one that's most commonly used, and that's the one that I want to teach you in this class, okay? So I've opened up ArcGIS. I'm going to go ahead and I'm going to create a new map. So I'm going to go over here and click on map. And let's call this CE 374U tutorial. And this is going to create a new map. Okay, and so it opens up and we can see a map of the United States. We can pan out with the mouse and we can pan in with the mouse just like you would with Google Earth or Google Maps. You can zoom into Texas and you'll notice it's showing us a couple of different things when we open up. We have what's called a base map layer. This is kind of just a base map that kind of allows us to get our bearings. We have two different base maps here, actually. We have the world topographic map, which I can turn on or off by clicking here. And we have the world hillshade, which kind of gives us a sense of the terrain and the elevation. So we can toggle those as follows. We can also change up the base map if we want. So if we want to change the default base map that's showing, we can go to map up here in the ribbon. And we can click on this icon here. This is the base map selector. And we can select, for instance, imagery. We can select aerial imagery and it changes the base map. We can zoom in and perhaps take a look at what I believe is Austin here. Actually, maybe not. So you can change the base map if you desire. I'm going to leave it on topographic by default because it's the cleanest and the easiest to work with for our purposes here. Okay, great. Was everyone able to successfully open up ArcGIS, toggle base map, those kind of things? Okay, cool. So what we're going to do next is we're going to download one of the data sets that I talked about at the beginning of class. Let's go ahead and just download a simple one, this US states data set. Okay, so that downloaded to my downloads folder. Let's go ahead and open it up. I'm going to go and extract it. So in my computer, you do that by going to 7-zip, extract to this folder, okay, and extracted to a new folder here. So I've downloaded this shaped file to my computer. What I'm going to do next is I'm going to go and add it to the map. Okay, so it downloaded to my downloads folder, to this folder called CB 2018 US State 500K 1. Okay, so what I'm going to do is to add this layer to the map, I'm going to go to this button here. I don't know why they made it so hard to find in this version of ArcGIS, but there is a button here called Add Data. You can see it here up in the ribbon underneath the map tab. And I'm going to click Add Data. And what it's going to do is it's going to ask me where that data is located. So I'm going to go find it in my file system. It's underneath Downloads. And it was under CB 2018 US State 500K. So note that if it doesn't appear, you can sometimes find it by hitting this refresh button, which refreshes the contents of the directory so that ArcGIS can find it. Okay, so that's that refresh button up here. So I'm going to go ahead and open up that file. Okay, so you'll see something that looks like this. And I'm going to go ahead and double click. And it loads all 50 of the US states in. Okay, and you can see it's loading them underneath over top of the base map. Okay, so we've now got a data set describing the 50 US states. So let me give you a quick overview of different GIS data types. There's two primary types of GIS data. There are vector files and there are raster files. Okay, so I'm going to tell you about each one of these files today. Today, we're just going to kind of give you a broad overview of GIS. And the next class, we're going to apply it specifically to the problem of watershed delineation, which is kind of more what we're going to be using it for in this class. Okay, but today I'm just going to give you kind of a broad overview of GIS. So there's two different data types. The first are vector files, and the second are raster files. So this here is a vector file. And it essentially is a collection of geometries defined by points that are connected by lines. So has anyone here used AutoCAD before? Okay, most of you here. So AutoCAD essentially represents geometry in the same way. You have a series of vertices or points that are connected by lines. A vector data set essentially consists of a collection of those geometries. They can be either individual points, they can be lines, or they can be polygons, which we're seeing here. Okay. And along with each of those geometries, we also have an associated table of attributes for each of those geometries. Okay, so we can kind of zoom around this map here. And if we click on one of these elements, let's just click on Texas, it'll bring up a table of information. Okay, so you can inspect these different geometries just by clicking on them. Here we have some information associated with Texas. So we have its postal code, for instance. We have a bunch of different identifiers, and we have the land and water area for the state in this table. Okay, so in addition to simply clicking on these different states, we can also select them. So if you go up here into map and you move here to select, you can now select different states by clicking on them. If you hold down shift, you can select multiple. Okay. And if you want to clear the selection, you can click this icon here. So this deselects all currently selected features. You can also select by a rectangular selection. And there's also various selection tools you can use, like line, for instance, if you want to select multiple states. I'm going to set it back on rectangle. Okay, so you can select different features, which we will be using later for processing. Okay, so as I mentioned, each one of these geometries has a set of attributes associated with it. And we can see those attributes by looking at what's called the attribute table. So I've selected these geometries. Let's go ahead and look at the attribute table for this entire data set. If I go over here to the left, towards this panel that's labeled drawing order, I'm going to go and right click. I'm right clicking this data set, and then I'm going to go to attribute table. Okay, and so this is a table basically that's showing all of the different attributes for our states. You can see that the ones that I selected kind of appear highlighted in this cyan color here in the table. And we can select out just the selected rows by clicking this button here on the bottom if we want to just look at the selected rows. I'm going to go back to show all records. Okay, so once we have that, we can do a couple things here. We can, for instance, click this button to zoom to our selection. We can invert the selection. And we can also copy the selection. So this is useful, for instance, if you want to go into Excel. Let's say we want to copy the selection and paste it into Excel. We can do that just like that, okay? Great. Okay, are there any questions so far on vector data sets? Yes. I have no idea, actually. A lot of them are just identifiers that are used for this data set. So this data set comes from the US Census. So a lot of these are internal identifiers used by the census that can be used to, for instance, join these tables with other tables. Yeah. So a lot of them are identifiers like GeoID, AFGeoID, and so on. You'll see that's pretty common in GIS, is that there will be various identifiers and keys that are used to join data together. Okay, great. So I'm going to go and exit out of this attribute table by clicking X. Okay. So one quick note I wanted to make. You can look at properties of your data if you right click on the data set over in this menu here and look at properties. So one property that I wanted to bring your attention to in particular is under source, spatial reference. So different data sets will have different spatial references defined for them. And it can sometimes be important to know which spatial reference you're using and whether it matches with another data set spatial reference. There are, in general, two different types of spatial references. There are geographic spatial references and there are projected spatial references. We'll get to this on Thursday's class, but in general, it's just important to know that if you are doing anything where you're computing the area of a geometry or computing its length, you'll want to use projected coordinate systems instead of geographic. Geographic is generally in degrees, latitude, longitude. Projected is in units like meters or feet. Okay, so that's just one thing to keep in mind for Thursday's class. Okay, cool. So I'm going to go and clear the selection here. Let's take a look at another data set. So I'm going to download another data set. So let's go ahead and look at this Texas precipitation regions. So I downloaded the data set. Let me go ahead and extract that one again. So we're looking, again, I downloaded Texas precipitation regions here. And so I downloaded and extracted it. And I'll give you a second to download that file. Okay. So I will go ahead and add it to the map again using add data. I'm going to go to downloads. I'm going to go to precipitation shapefile. Okay. And it loaded this shapefile. So what these bands represent, these are different precipitation regions for the state of Texas. Okay. So each one of these bands within this shapefile represents a different average precipitation per year. Right now, though, it's kind of hard to interpret it because they're all kind of this beige color. Okay, so it's not really giving us very much information. So what we're going to do is we're going to color these different bands according to their precipitation level. Okay. So to do that, first, let's take a look at the attribute table. So this is just like the other data set, this is a collection of different polygons. If we look at the attribute table, we'll see that there's a couple different fields here. This FIPS here, this is the state code, so it's probably for Texas. But then it also has this column called precip inch. Okay, so that corresponds to the annual precipitation within each one of these polygons, okay? So what we're gonna do is we're going to color the polygons by their precipitation value given by precip inch. Okay. So to do that, we are going to right click on the data set and we're going to go to this menu called symbology here. So I'll give you a second to follow along. We right clicked on the data set and now we're going to go to symbology. Okay, and you'll see that what happens when I click on that is that it shows that there is just a single symbol that's being used for our symbology. Okay, so what I'm going to do is I'm going to change from single symbol, I'm going to change to graduated colors. Okay, and by default, it already selected precip inch as the field to color based on. So that is already correct. There's a couple things I want to change about this. First, this color scheme doesn't really convey the information we want here. Let's change it from red to blue. Okay, so I'm going to go to color scheme. I'm going to go to a blue color map. Let's just pick this one here. Okay, so that looks much better. And there's a couple other things we can do here. On the method, it gives you various methods for breaking up the colors into different bins. I'm going to change it from natural breaks to equal interval. So this divides up the precipitation values into equal sized bins and colors based on those bins. And finally, I'm just going to increase the number of classes here. I'm going to increase it to, let's say, 8 different precipitation classes. Okay, and so you get a little bit more gradation in the color map. Okay, and you should get something that look like this. And now you can see that the precipitation in Texas is, it varies pretty dramatically from east to west. Okay, with east being much rainier than the west. Okay, I'm going to go around and I'm going to just check on you and see how you're doing. How many people were able to successfully change the color map? Well, is anyone having any trouble with that? Any trouble? Uh-oh. Okay. I'll be back up here in about 2 minutes. I'm just going to go over and check on different people. Okay, everybody. I just want to make it through the next couple of things pretty quickly, and then at the end, I'm going to give you a chance to experiment with ArcGIS. I want to just cover a couple of things really quickly so that we're all on the same page. Okay, so we have this nice colored version of Texas that is colored by the precipitation region. I want to show you another thing we can do here. So let's say we want to take this map and we want to select just the rainiest regions of Texas, and we want to isolate that as its own shapefile. So we can do that by working with the attribute table. So we right click on our data set. Okay, we can go to attribute table and we can select different elements of our data set based on the values that are in this table. So what I'm going to do is I'm going to go to select by attributes. Okay, I'll just do that again so you can see what I'm doing. So what I did was I right clicked on here. I went to attribute table. And then down here, you'll see a button that says select by attributes. Okay. Is anyone having trouble finding this button? Everyone got it? Okay, so what we're going to do is we're going to select by attributes. And this is going to bring up a form where we can query different attributes of the table. So what I'm going to do is I'm going to say, we're going to select all of the rows from this table where precip inch is greater than, let's say, 30 inches. Okay, and I'm going to go ahead and hit apply. Okay, and you'll see that it selects the regions in Texas where the precipitation is greater than 30 inches per year. Okay. Okay, so is anyone having any trouble finding how to query attributes from the table? No? Okay, good. So next, what we're going to do, this is sometimes a useful thing to do for GIS analysis. We're going to take this subset that we've selected and we're going to export it to its own shaped file. So what I'm going to do is I'm going to go over here to this tab that says data up on the top. I'm going to click on that tab. And I'm going to say layer from selection. So it says make a copy of this layer using just the currently selected features. Okay, and so I went ahead and did that. And now you see that if I turn off the other data set, you can see that we have just the regions in Texas where the precipitation is greater than 30 inches. Okay, so this is a very useful operation that you will be using later on. Okay. Okay. Yes.
Can you show that last step one more time?
Yes. So what I did was I selected these from the table. I went up here to data. And yeah, there we go. I have to make sure this is your original data set is selected. Go to data and then do layer from selection. And once you click that, it'll automatically just populate it over here on the left. And you get this subset here. Okay, so I showed you vector data sets. The other kind of data set that you use in GIS is called raster data. Okay, so I'm going to go ahead and download a raster data set. Actually, I already have it downloaded, and it takes a little bit longer to download, so I won't do it here. But I'm going to use this Texas impervious area data set here. So go ahead and download that one yourself. Okay, and I'm going to go load it into the map. I'm going to say add data. And I know that this is, I'll just find where it is in my system. It is under Texas impervious area, Texas impervious area.tiff. Okay, so as I mentioned, there's two different types of files that you use in GIS. The first is vector data sets, which are a collection of geometries defined by points and lines. And the second are raster data sets, which are essentially a grid of pixels. Okay, so you can think of a raster data set as basically being an image. And this here is a TIFF file, which you may know is also an image file type. Okay, so a raster data set is a collection of pixels. This raster data set here is a collection of pixels where each pixel represents the percent impervious area for that pixel. So you can see here, I've isolated it to just Texas. If we go and zoom in, we can see the impervious percent for each pixel in Texas. Okay, so if you click here, for instance, you'll see that this has an impervious percent of about 0. So these kind of darker areas have an impervious percent of about 0. But if you go into these urban areas and you click on these red or purple pixels, you'll see that they have impervious area percentages in the range of 70 to 100%. So this red pixel here was 70. This purple pixel here is about 98%. Okay, so what I'm going to do for the rest of the class is I'm going to kind of let you explore with these different data sets. So I've got US states, US urban areas, precipitation regions, impervious area, and land cover. And I'd like you to just kind of explore the interface, just see the different tools you can use on these different data sets. And for those of you who want a challenge, I have one challenge for you. So I want you to download this urban areas data set. I have it loaded up here already. I've downloaded this urban areas data set. Open up the urban areas data set. So what I want you to do is I want you to pick an urban area in Texas. So this, for instance, is Houston right here. And I want you to figure out how to compute the average percent impervious area for an urban area in Texas, for one of these defined urban areas in this shapefile. Okay, so that is my challenge to you. If you don't want to take on this challenge, then just explore ArcGIS for the remaining 5 to 10 minutes, and I will walk around and answer any questions you have. Okay? Yes. So the challenge is pick one of these urban areas in Texas defined by this shapefile. And what I want you to do is to compute the average percent impervious area within that urban area from the impervious raster. Yeah.